We're going to do a problem about finding the composition of a mix of enantiomers. This was a question by a student. So I'm going to copy what is here on the question. And it says there is two bromobutane. I'm going to say R2-bromobutane. And then the rotation, the optical rotation of that is negative 23.1. And then the question says, what is the ratio for the, say, composition ratio of enantiomers, if the observed rotation is plus 18.5 degree. Okay, so let's first, for the sake of our structures, draw a structure first for our IUPAC, right? So butane, 1, 2, 3, and 4, right? And so it says 2-bromobutane, and it is the R. So I'm gonna just put it over here, bromine, right? So, and if we assign priorities, remember that here, the hydrogen will be on the box. So say priority 1 is bromine, then the ethyl, then the methyl. So I'm gonna go 1, 2, 3. See, I'm gonna rotate clockwise. So that's actually the R. So that's a compound, and it says it has this optical rotation. So first, we see the sign here. Notice that the R enantiomer has a negative 23.1 optical rotation. However, the observed has a plus sign. And we know that the optical rotation for the S enantiomer will be exactly that amount, but it will be plus 23.1. What that means is that in this mix, we will have an excess of the S enantiomer because, again, the net optical rotation has a positive sign. So we know that we have an excess of the S enantiomer. But by how much? Let's do that. So the first thing that we're going to do is calculate what we call the percent enantiomeric excess. So by how much in percent? Percent enantiomeric excess. What we're going to do is now divide the observed rotation. So I'm going to write it down, say observed optical rotation over, and we're going to do that in absolute value. And then over the rotation of, say, the pure enantiomer, again, absolute value, times 100. So that will tell me how much in excess is one respect of the other. So the percent enantiomeric excess this time then is going to be 18.5. Again, I'm just going to put the bar so you remember is absolute value. And then 23.1 here, and then times 100. And that gives you 80. So we have 80% more of the S. Remember that we, by the sign, have already determined that the S enantiomer was in excess. Okay, in what? How much in excess? By 80%. So now we're going to use this to calculate the, say, the composition of the mix. Now we know one of them is going to be, say, the R, which is in less amount, say X amount. And then the one in excess is going to be X plus 80. Again, I'm going to say that sum of that is 100. Again, this is the one in excess, right? Which in our case we know is the S. This is the one in less amount. So all of that. And we know the sum is the 100%. So again, X for the R, the other is in excess by 80%. So all we need to do now is solve for X. So here you have 2X is 100 minus 80. And so X equal 10. You do solve for that, right? 2X equal 20. And then solving for X gives you that. What that is the composition then of the mix is we have 10% of the R, and of the S, we have 10 plus 80. So we have 90% S. So that is the composition of the mix. Again, what we did is we use the optical rotation of the pure enantiomer. It doesn't matter if it is the R or the S, or say the sign of the optical rotation, because we're using absolute values here. And then what we did is calculate first the percent enantiomeric excess by using the optical rotation, the observed over that of the pure enantiomer times 100. And then to know the composition, remember that we need to take into account what is the sign of the observed rotation. If we know that the pure R enantiomer has an optical rotation of 23 minus 23.1, then the S will have the other sign, plus 23.1. So that's the one in excess because the observed rotation has a positive sign. So after we do the calculation of the enantiomeric axis, and here it is, 80%, I know that the one in less amount, the R is X, and the SM will be X plus 80. Solving for X give you 10, so the R enantiomer is 10%, and 90 is the S.